Hey friends, welcome to the YouTube channel All About Electronics. So in this video, we will learn about the ECL logic. So we will see that what is ECL logic, the advantages of this ECL logic over the other logics, and the basic working principle of the ECL logic. And then after, we will also see the circuit of one of the popular 10K series of ECL gate like the OR and the NOR gate. And through that, we will understand the working of the ECL logic. So this ECL logic is also known as the emitter coupled logic. So similar to the TTL logic, it also uses the bipolar junction transistors. But if you recall, in the TTL logic, the transistors were operating in the saturation during the switching. So of course, in the advanced TTL logics, the transistor saturation was prevented. But if you see the conventional TTL logic, then here the transistors are operating in the saturation. But this ECL logic is the non-saturated logic. That means here the transistors do not operate in the saturation. So because of that, there won't be a charge storage issue in the base of the transistor, and hence the speed of the operation will be faster. And moreover, here the voltage swing is also very low, meaning that here the difference between the logic low and the logic high is also very low. So therefore, here the parasitic capacitance will also charge faster, and hence these ECL logic gates are very fast. But here, since it is a non-saturated logic, so transistors are always operating in the active region, and therefore the power consumption of this ECL gate will be higher. Now the reason this logic is called the emitter coupled logic, because here the emitter of the transistors is coupled or connected together. So typically these ECL gates are used in the high-speed applications like in the clock distribution system and in the high-speed data communication systems. So in the early days, they were also used in the high-speed computation. But because of its higher power consumption, nowadays, they are not used in the applications where the energy efficiency is more important. And rather, they are used in the applications where the speed is more important than the power consumption. So now, let us see the basic element of this ECL logic gate, and let us understand the basic working principle of this ECL logic. So the basic element of this ECL logic is the differential amplifier, and here this differential amplifier is used as the current steering switch. That means here, by changing the input voltage by the small amount, it is possible to steer the entire current from the one arm of the differential amplifier to the other arm. And for that, here the one arm of the differential amplifier is biased with the fixed voltage. Let's say that is equal to VR, and the input is applied at the second arm. And here we are assuming that the transistors used in the differential amplifiers are the matched pair. That means in all respect they are identical. Now whenever this Vin is equal to VR, then the current through both arms will be equal. So here as you can see, at the emitter of this differential amplifier, the current source is connected. So if Vin is equal to VR, then the current through both arms will be equal to I by 2. But if this Vin is slightly more than the VR, let's say this VR plus delta V, then the entire current will flow through this branch. That means this entire current I will flow through this transistor. So at that time, if we see the VO1, then this VO1 is equal to VCC minus this I times RC, that is the drop across this resistor. And similarly, if we see the VO2, then that will be equal to VCC, because this second transistor remains in the off condition. And similarly, when the input is equal to VR minus delta V, then the entire current will flow through this second transistor. So at that time, if we see the VO2, then the VO2 will be equal to VCC minus I times RC. And if we see the VO1, then this VO1 will be equal to VCC, because this transistor will remain in the off condition. So in this way, by changing the input voltage by the small amount, it is possible to steer the entire current in the one branch. So very shortly we will see that what should be the value of this delta V, so that it is possible to steer the entire current from one branch to the other branch. But in this way, because of the current steering, we are getting the two possible output states. So one is the VO is equal to VCC and the other is equal to VCC minus I times RC. So due to this current steering capability, sometimes this logic is also referred as the current steering logic or the current mode logic. So here if you observe, then although there is a current switching, but the total current drawn from the supply remains constant. That means at any given time, the current drawn from the supply will be equal to I. And therefore, unlike the TTL or the CMOS logic, there will not be any current spikes during the switching. And that is one of the advantage of the ECL logic. Moreover, if you see the earlier ECL logic gates, then they were using the negative power supply. That means in that case, this VCC will be equal to 0. And instead of the ground, we will have the negative voltage. So in that case, if we see the two possible output states, then these output states will be equal to 0 at the minus I times RC. So as you can see, in this case, even if there is a variation in the power supply, then also it won't affect the outputs. Because here, we are taking the outputs between these nodes and the ground. And in this way, by using the negative power supply, the fluctuations in the power supply line will have the minimum effect on the output. And that is why, even though this ECL logic has the low voltage swing, then also it will work properly. And in a way, it is possible to use this ECL logic in very high speed applications. But the thing is, here this differential pair is the basic element of any ECL logic gate. And as you can see, here this differential pair is used as the current steering switch. So now let us see, in this differential pair, what should be the value of this delta V. That means by changing this input voltage by the watt amount, it is possible to steer the entire current from one branch to the another branch. So here, first let us assume that the beta of these transistors is very high. So we can assume that the emitter current of these transistors is same as the collector current. So here, let's say the two transistors are Q1 and Q2 respectively. So here, if the VBE1 is the drop across the base emitter junction of the Q1, then we can say that this IE1 is approximately equal to this IS times e to the power this VBE1 divided by VT, where this VT is the thermal voltage. And similarly, for the second transistor, this emitter current IE2 is approximately equal to this IS times this e to the power this VBE2 divided by VT. So if we take the ratio of these two equations, then we can say that this I1 divided by I2 that is equal to this e to the power this VB1 minus VB2 divided by VT. So now let us take the natural log on both sides. So if we take the natural log on both sides, then we can say that this VB1 minus VB2 is equal to this VT times this natural log of this current I1 divided by I2. So here basically we need to find the value of the delta V. So if you observe over here, then the emitter of both the transistors are connected together. That means here the V1 and the V2 are equal. So we can say that effectively that is equal to this VB1 minus VB2, and that is equal to this VT times natural log of current I1 divided by I2. So here this total current, that is I1 plus I2, is equal to I. So here let's say when the Vin is equal to VR plus delta V, at that time this current I1 is 99% of the I. And of course at that time this I2 will be equal to 1% of the I. So we can say that when this Vin is equal to VR plus delta V at that time. This IE1 is equal to 99% of I. So at that time, we can write this expression as this VB1 minus VB2, that is equal to this VT times natural log of this 99 divided by 1. Now as you know, at the room temperature, the value of this VT or the thermal voltage is equal to 25 millivolt. So if we calculate the value of this VB1 minus VB2, then that is roughly equal to 115 millivolt. So we can say that when this input voltage is 115 millivolt above the VR, at that time the 99% of the total current flows through this Q1 transistor. So as you can see, even by changing the input voltage, even by this 115 millivolt, it is possible to steer the entire current from one branch to the other branch. And that is why it is possible to operate this ECL logic even with the low voltage swing. So of course, this circuit alone won't work as the ECL gate, because in the actual circuit, we also need to generate this reference voltage, and we also need to make sure that the logic high and the logic low voltage levels are also identical for both input and the output side, so that the output of the one logic gate can be connected to the another logic gate. So if you see the commercially available ECL gates, then in that this 10K and the 100K series are the very popular. And of course, nowadays, the different versions of this series are also available. So in these ECL gates, when they are operated with the negative voltage, then the reference voltage is kept around minus 1.3 volt. And if we see the logic high and the logic low voltages, then they are plus minus 400 millivolt around this voltage. So if we see the logic high, then that is around minus 0.9 volt, and the logic low is around minus 1.7 to minus 1.75 volt. That means when the ECL gates are operated with the negative voltage, then the logic high and the logic low voltages are the negative voltages. And here, this is the circuit of the ECL 10K series 2 input OR and the NOR gate. So as you can see, one of the advantage of this ECL gate is that the output and its complement are available at the same time. That means using the same circuit, it is possible to get both OR gate as well as the NOR gate outputs. So here, this part of the circuit is the current steering part. So here, since it is the 2 input gate, so here this A and the B are the 2 inputs. And as you can see, here these 2 transistors are connected in the parallel, so that it can perform the OR and the NOR operation. That means here, these 2 transistors are the input transistor, while if you see the third transistor, then that is the reference transistor. And these 3 transistor forms the current steering switch. Now one more thing, if you observe over here, then here the one end of the supply is connected to the ground terminal, while the other end is connected to the minus 5.2. That means here the negative supply is used in this ECL logic. And here the reference voltage for this transistor is generated using this part of the circuit. And if you see this last part, then that is the emitter follower. So this part performs the level shifting that is required for getting the desired output voltage. Moreover, since it is the emitter follower stage, so it also provides the low output resistance to the load, and in a way it offers the faster rise time. So in this circuit, to make the parasitic capacitance lower, the size of all the transistors were kept small. And hence, we can assume that the base emitter voltage of all these transistors in the circuit is around 0.75 volt, and the current that is flowing through the emitter is around 1 milliampere. So assuming that, first let us see how this reference voltage is generated for the given circuit. So here we will assume that the drop across each diode is around 0.75 volt. So in that case, we can say that the current through this branch, let's say that is equal to IR, is equal to minus 5.2 volt, plus the drop across these 2 diode, that is plus 1.5 volt, divided by the sum of these 2 transistors, that is equal to 4.98 kilo ohm plus 907 ohm. And here, to find this voltage VR, first we need to find the drop across this resistor. So we can say that that is equal to this IR times 907 ohm. So if we calculate, then that is roughly equal to minus 0.57 volt. That means here the voltage at this node is equal to minus 0.57 volt. And on top of that, if we add the voltage drop VBE, that is 0.75 volt, then this voltage VR is equal to minus 0.57 volt minus 0.75 volt, and that is equal to minus 1.32 volt. So that is how the stable reference voltage is generated for this reference transistor. So now let us see, when both A and B inputs are logic low, then how the circuit will behave and what outputs we are getting. So earlier we have seen that the logic low voltage is around minus 0.4 below the reference voltage. So that is around minus 1.7 volt. And similarly, if we see the logic high, then that is zero point 0.4 volt above the reference voltage. So that is around minus 0.9 volt. So here, first let us see how the circuit behaves when both A and B inputs are minus 1.7 volt. So here, let's say these three transistors are Q1, Q2 and Q3. So whenever both A and B inputs are logic low or around minus 1.7 volt, at that time this Q1 and Q2 will remain in the off condition and the entire current will flow through this Q3 transistor. Now here if you observe, then instead of the current source, at the emitter terminal we have the resistor. That means here we will have the slight variation in the current depending on the voltage at the emitter terminal. But that change will be marginal. So here when this Q3 is on, at that time, first let us see the emitter current. So here we have seen that this reference voltage is equal to minus 1.32 volt. And here we assume that this VBE is equal to 0.75 volt. So we can say that this emitter current is equal to minus 5.2 volt, that is this voltage, plus 0.75 volt, that is this VBE drop, plus 1.32 volt. And in the denominator we will have this resistor, that is equal to 779 ohm. So if we calculate the value of this emitter current, then that is roughly equal to 4 milliampere. And here, assuming that this beta is very large, this collector current will also remain almost constant. So we can say that when this Q3 transistor is in the on condition, then its collector current is roughly equal to 4 milliampere. That means here, if we see the drop across this collector resistor, then this Vc3 is roughly equal to minus 4 milliampere times 245 ohm, that is roughly equal to minus 0.98 volt. While if we see the other output or the voltage at the collector of the Q2, then just by looking at this part of the circuit, we can say that that is equal to 0 volt, because this resistor is connected to the ground terminal. That means we can say that when the A and B inputs are minus 1.7 volt, then the one output is equal to minus 0.98 volt, while the other output is equal to 0 volt. But here we have just seen that for the ECL logic, the logic low is equal to minus 1.7 volt, while the logic high is equal to minus 0.9 volt. And we know that if we want to use this ECL logic gate in the circuit, then the input and output should have the same logic low and the logic high levels, right? So to make the outputs of the ECL gates compatible with the logic high and the logic low levels, the one more emitter follower stage is used. So this stage serves the two purposes. First is, it performs the required level shifting to get the desired voltages for the logic low and the logic high. So for example, here when both A and B are logic low, at that time, the voltage at this end is equal to minus 0.98 volt. But now, because of this emitter follower stage, we will also have the drop across this resistor, that is roughly equal to minus 0.75 volt. That means here, if we see the VO2, then that is equal to minus 0.98 volt minus 0.75 volt, and that is roughly equal to minus 1.72 volt. So that is very close to logic low. And similarly, if we see the VO1, then that is equal to the voltage at this node minus 0.75 volt. So this VO1 will also be roughly equal to minus 0.8 volt. So in this way, because of this emitter follower stage, we are getting the proper logic high and the logic low levels. So here as you can see, this VO1 and the VO2 or the outputs of this ECL gate are kept open. But in the actual circuit, either they are connected to the other ECL gate or they are connected to the output load. So typically in this ECL gate, the transmission line will act as a output load and it will have the resistance of the 50 ohm. So whenever the output to this ECL gate is the transmission line, then this transmission line is terminated with the voltage of minus 2 volt. So depending on that load, we will get the value of this VO1 because that load will decide the drop across this resistor. Because the drop across this resistor is equal to the current that is flowing through this emitter of this transistor divided by beta. And therefore, depending on the load, this VO1 will slightly change. But typically, it is around minus 0.8 to 0.9 volt. And in this way, this voltage can be considered as the logic high. So here, if you see the output VO2, then it will act as a OR gate. Because whenever both inputs are low, then this VO2 will be minus 1.72 volt and that can be considered as the logic low. And likewise, when both A and B are high, then this VO2 will also be high. And on the other hand, this VO1 output will act as a NOR gate output because here when both A and B inputs are low, then this VO1 will be equal to roughly minus 0.8 volt and that can be considered as the logic high. So in this way, through this VO1 and the VO2, we are getting both complementary outputs at the same time in this ECL gate. So now, let us see the other case when both A and B or any one of them is 1. So in that case, the input voltage to this A and B input will be equal to minus 0.9 volt. So in that case, either Q1 and Q2 will be on while the Q3 will remain in the off condition. So here let's say this A is equal to 1 while the B is equal to 0. That means here this A input is equal to minus 0.9 volt while the B input is equal to minus 1.7 volt. So in this condition, the Q3 will remain in the off condition and the entire current will flow through this branch. So in this condition, now let us find the emitter current. So here this base voltage is equal to minus 0.9 volt and here if we assume the VB drop of 0.75 volt, then this emitter current IE will be equal to minus 5.2 volt plus 0.75 volt, that is the VB drop plus 0.9 volt, and in the denominator we will have this 779 ohm. So if we calculate the value, then this emitter current will be roughly equal to 4.55 milliampere. And in that condition, the drop across this 220 ohm or this VC2 will be equal to minus 4.55 milliampere times 220 ohm. So that is roughly equal to minus 1 volt. So because of that, if we see the output voltage, then that is equal to minus 1 volt minus 0.75 volt. So that is equal to minus 1.75 volt. While if we see the VO2, then that is equal to minus 0.75 volt minus the drop across this 245 ohm. So that will depend on the load. So let's say the current through the load is equal to IE. So in that case, the drop across this 245 ohm will be equal to I divided by beta times 245 ohm, and roughly it will be equal to minus 0.8 volt. That means in that case, this VO2 can be considered as the logic high. So in this way, when the A and B inputs or any one of them is high, then this VO2 output will be high while the VO1 output will be low. And in this way, this VO2 output will act as a OR gate and this VO1 output will act as a NOR gate. And in this way, this circuit performs the function of the OR and the NOR gate. Now here, if you observe this circuit, then here the 50 kilo ohm resistor is connected at the input side. That means here the one end of the 50k resistor is connected to the input terminal while the other end is connected to the negative power supply. The reason is that the voltage swing in the ECL is very low. So if the input is left open, then also due to the external noise or the interference, we may get the false logic high or the logic low. So to avoid that, this 50 k ohm resistor is connected. So in this case, through the 50 kilo ohm resistor, the input will get tied to the negative power supply. That means here, even when the input is not applied, the input will be considered as the logic low. And in this way, we will not get any false logic high. So that is the purpose of these resistors at the input side. The another thing if you observe, then here this emitter follower stage has the separate ground. The reason is that these outputs are connected to the external circuit or the load. And on these outputs, there will be a frequent change in the voltage level from logic low to the logic high. So this change should not affect the other part of the circuit where the stable reference voltage is generated. So that is why for the current steering as well as for generation of the reference voltage, the separate ground is used. So of course, externally, when we connect the circuit to the ground, then all the grounds will get common. But internally in the design, they are kept separate to minimize the interference. So I hope in this video, you understood the basics of the ECL logic. Like what is the basic principle of the ECL logic, the advantages of the ECL logic, and the different applications of the ECL logic. And I hope through this circuit, you also understood the basic working of the ECL gate. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.